Folks have asked me to make a little video about Riemann sums and this process so they could watch it multiple times. So let me review what we've talked about. So we got these things called Riemann sums, and the idea is that they are an answer to the area problem. They let us calculate an area under a curve. So the context is we've got a positive function f on an interval from a to b. I guess I'll draw a picture over here. So let's put the domain interval here. Function value starts there, ends there. Let's say the graph of the function looks like that. I'm just going to highlight the edges, and this is a region, right? There's a region here between the curve and the x-axis, and we want to calculate that area. And a lot of times we call this calculating the area under the curve. And that's technically the area between the x-axis and the graph of y equals f of x. Area under the curve. If our curve were straight, we've talked about this before, that'd be easy to do. We could use plane geometry, but the graph here is curvy, and we can't use plane geometry. We actually have to use calculus. So I'm going to outline for you the method that we've been using, and I'm going to outline it in 3 steps. So the first step is we're going to approximate the area. Oops. Using rectangular or rectangles by slicing the region into strips of equal width and summing. So that's step 1, is that we're going to cut up the region, and then on each slice we're going to put a little rectangle, and then we know what the area of a rectangle is. The formula is easy, like the area of a rectangle is its length times its width. And then we're going to add up the area of those rectangles, and the total area of the rectangles is approximately going to be the area under the curve. The summing here, right, this is where we'll pull back in that Riemann notation. The second step in the method is called using the method of exhaustion. So this is a classical title for this process. What we do is we look at the sum, and by that I mean this sum right here. Look at the sum, and we take its limit. As the number of rectangles increases. Okay, and increases without bound. So when we cut this region into strips, we cut it into a finite number of rectangles, and each rectangle has the same width. And so as we increase the number of rectangles, each rectangle gets narrower and narrower. Right? They start wide, and then they shrink and they get narrower and narrower. And as they get narrower and narrower, the sum of the areas of those rectangles get closer and closer to the area of the region under the curve. And in fact, that's the end. That's the result of this method, is that the area of the region equals the limit of this sum. Okay, and that leads us to an idea of what we call the definite integral. All right, so this is the method we'll go through, the conceptual method we go through to solve the area problem. We cut up the region into strips of equal width, and we add them up. And then we look at that sum and we say, oh, well, what happens if the number of rectangles increases without bound? That's the method of exhaustion. I'm increasing the number of rectangles. Increasing and increasing and increasing. Then I look at that limit, and the limit is the area of the region. All right, so let's put some notation on this. Okay, so here's step A. So we're in part 1 of our method, and so step A is we have the region. So let me draw our picture again. I think it looks something like this. We want the total area of the approximating rectangles. So we're going to fix a value for n, and n is the number of rectangles. I've worked a couple examples where n has a particular number, but here I just want you to think of n in the abstract. Just fix a number n. We're going to keep the symbol here n representing that number. And we're going to define delta x, the width of each of our rectangles, as 1 over n times b minus a, right? That's the same thing. So that's the length, or that's the width of each rectangle. But the way I'm going to think about it right now for this moment is I'm thinking in terms of this interval here, and I'm chopping this interval up into pieces. I'm chopping it up into n pieces of the same width, and the width is going to be delta x. So each of my pieces, each of my subintervals here is going to have width b minus a over n. In the places where I cut my interval into subintervals, I'm going to call these partition points. And I'm going to label the partition points to be x0, x1, x2, x3, and so on up to xn. This first partition point is going to be my leftmost endpoint, and the last partition point is my rightmost endpoint. And the distance between each of these partition points, of course, is the width of each subinterval. It's delta x. Okay. So because each interval is delta x long, the ith partition point is delta x away from the previous partition point. And if you like, you can stack those up together and say the ith partition point is I lengths away from the leftmost partition point, right? The leftmost endpoint here. So these are equivalent. On the ith subinterval, so we're going to do this for each subinterval, and here I'm saying just pick one. On every subinterval, we're doing this. On the ith subinterval, we'll build a rectangle that is delta x wide, and now watch this, f of xi tall. So let me show you on the picture what that looks like. So I'm going to put the endpoints for the ith subinterval here. And these partition points are where we make our slices. So think of our region as being sliced these two places. So I'm going to put a rectangle here. And I'm choosing to use the right endpoints. So my rectangle is going to be this tall. I'm going to use the function at the right endpoint. So here's the height of the rectangle. And it's going to be this wide. So here's my rectangle. Okay. The area of the ith rectangle, this rectangle I just drew, I'm going to call that a sub I. So we'll put that a sub I in there. Well, area is the length times the width. Now we do this for each of the subintervals here. We're going to have n of them. So the area the total area of the region under my curve is approximately the sum of the areas of the rectangles. So if we look in this picture, on this slice here on the ith interval, I should look to see if I got another color here. The area of my region is right here. It's in the blue. And the area of my rectangle is pretty close to that. The difference is this part right here. So the area of the rectangle and the area under my curve are, on this slice are not exactly the same, but they're pretty close. Here's the error. Okay. So that happens on each of the rectangles. So if you add up the area of the rectangles, this is approximately equal to the area under the curve. So the area of my region is approximately equal to, like I said in the last page, you add up all the areas of the rectangles. But this is exactly exactly where sigma notation comes in handy. So I can rewrite this as the sum of my AIs, where I goes from 1 to n. Right? This is sigma notation for this, right? I got the ellipses, the dot, dot, dot. And now here, I can also write in my formula for my areas of each rectangle. And this, my friends, is what we're going for. This expression right here is called a Riemann sum. using n rectangles. And if we want to put a fine point on it, we could say and left endpoints. Because here these xi's, these are the left endpoints of the subintervals we've created. So here's our picture. On the ith subinterval here, I used its left endpoint. Oh, right endpoint. My right and left are mixed up again. I'm using the right endpoint to determine the height of my rectangle. Okay. And that's basically it. So if you see a sum that looks like this, you are talking about a Riemann interval. So a Riemann sum. So to summarize, the area under a curve y equals f of x of a continuous positive function on an interval AB is approximately the sum as I goes from 1 to n of f of xi delta x, where delta x is 1 over n times b minus a, and xi equals a plus I times delta x. That's a Riemann sum. Next, I'll do a couple examples of some Riemann sums to help you get a feeling for how this all works. But this is the process that we use, that I often like to refer to as cutting up and adding up. You take a region under a curve, slice it up into slices of equal width, and look at the rectangles on each of those subintervals, calculate their area, and the sum of those areas is your approximation of the area of the region. Okay. So hopefully this is helpful. I'll make another screencast with some examples. See you then.